All right. So we started this assignment last week, Kalman Filter assignment. So today we'll spend some time on Kalman Filter because this is extremely important, even beyond the exam, right? I want every one of you to develop this skill, how to code a Kalman filter, how to develop a Kalman filter based system in MATLAB, okay, because it's extremely important whenever you have to deal with sensors and all, right? So take it very seriously. So this assignment has a few parts, A, B, and C. I will straight away go to C, right? This is the problem, right? I will briefly describe the problem. So a spacecraft is accelerated by bursts of gas, uh, right? Ejected by its reaction control thrusters. The position, velocity, and acceleration of the spacecraft are denoted by P dot K, and AK, position, velocity, and acceleration, okay? At discrete time K. So every discrete time interval, right, capital T, you evaluate the position, velocity, and acceleration, okay? The motion is because of the bursts of gas ejected by the reaction control thrusters, okay? So you're asked to write expressions for pk plus 1. So position at k plus 1, if you know the position at pk, okay, sorry, at k moment, and velocity, and show that the state space model of the spacecraft is this. In fact, to help you, the state space model, discrete model, is actually given here, right? But you are supposed to derive it. So if you are unable to derive, you can skip the part and take the model given and go ahead. So that is how the question is designed, right? Not to make you stuck because you don't know how to answer this particular part. Okay, right. And then the second part. So let's work out the first part first, right? And before that, you are asked to write the Kalman filter algorithm describing each of steps, right? So we'll go to the assignment, Kalman filter. It's over here. These are the steps of the Kalman filter. Don't have to memorize, right? But you need to understand what these 5 steps are, right? The first one, uh, now first actually not a step, it is a process here, right? You need to have the process identified in terms of its discrete state space model. Xk plus 1 is equal to uh, uh, phi xk plus wk, and this is actually the disturbances to the plant or unmodeled dynamics, actual motion that is not modeled, okay? And then zk is equal to h xk plus vk. This is the sensor noise. This is how you pick up out of the state variables which of these sensors are actually measured, okay? And this is the sensor measurement. It can be just one signal that you measure, or it can be a number of sensors, right? 2, 3, like that. And now Kalman filter is going to actually produce all of the states, including the measured ones, okay? It's not that you use the measured ones and use the Kalman filter to generate others. No, it's not the case. Kalman filter generates all of these states, including the measured ones and the unmeasured ones, okay? Right. Right. So this is actually the first step of the Kalman filter, right? Look at the equation. It is simply this part here in the process model. Using the initial state and the the state transition matrix, you actually estimate what is the future state is going to be. Okay, and you put a negative sign because this is not the final one. This is only the first estimate. For x hat k, which is the starting point, because otherwise we don't know anything, no? So you have to start with some initial conditions, right? So yes, they are. Second step is p minus k plus 1. So this is the, now you are doing an estimation process, right? You are the estimator now. You are telling this is the most accurate value, okay? And also you say it's not perfectly accurate. There is some sort of variance in that prediction. Okay, it's moving back and forth, and there's a spread in that estimation, right? Spread means there is actual value, ground truth, true value, and your estimate is actually sticking around it. So how big that area is where you estimate is hanging around is kind of covariance. Okay, so this is this one, and it's also minus, which means it's not the final one, it is predicted one. This is the equation for that. And the third one is the Kalman gain. Okay, you calculate the Kalman gain using this equation. What the gain does is that it tries to combine the measurement of the sensor reading actually together with your prediction using the dynamic model. There you have a model, right? You have a model here, and using the model you calculate xk plus 1 estimate, and also using the sensor, right? You sense it, you measure it. So you have the model prediction of the state, and also you have the sensor reading of the state, right? Two values for the same quantity. Two values for the same quantity. So that's why you need the gain to decide how much you trust the sensor and how much you trust the process estimation. You know the previous state and you want to calculate the present state. You can do that using the system dynamics, and how much you believe that, right? And how much you believe the sensor. So that sharing is done by this gain. So after that, you can actually predict your state. Now you know how much you want to trust the sensor, how much for the state prediction, right? Then you can actually estimate the state x hat k plus 1 using this equation. Now there you can see the Kalman filter, Kalman gain comes over here from here, right? It is the measurement minus this one. Measurement minus this one. So this one is the previous estimate xk plus 1 over here, right? And then you actually get number of states, not everything, depending on how many of these states are actually measured. Same ones that you measure, you bring it over here and see the difference. Okay, the difference is multiplied by the gain. Okay, so that's what you do. Once you do that, you update your measurement covariance, right? So measurement covariance is a thing, as I said, this is the predicted one, this is the actual one. It is minimized in the Kalman filter derivation. It doesn't allow the error prediction, the variance of error prediction to grow. It is actually minimized. So these are the 5 steps, right? You can use the 5 steps in MATLAB and actually code the Kalman filter, right? Then we start with the problem given to us, right? Now, you know the dynamics, right? When you have an acceleration, how velocity changes and then how the position changes. So pretty simple. Position k time k plus 1 is actually the position at k plus velocity times time t, okay, plus half acceleration times t square. This is the motion dynamics. Everybody knows it. You just write the equation. So that is for the position. And what about velocity? Velocity is the velocity now plus acceleration times time. That is how velocity changes, right? Because of an acceleration. So both these equations are pretty simple equations. Anybody can write it, okay? Anybody can write it. How acceleration affects the velocity and how acceleration affects the position, right? Now you want to put these two equations into matrix form. So you create a column vector here, P and P dot, and here also P and P dot, because this is K time K, this is time K plus 1. All right. So from this equation, you get Pk and P dot K. So therefore, the first row is 1 and T, 1 and T. And for the second row, it's 0 and 1, 0 and 1, like that. Plus, you have this half AKT square for the first row and just AKT for the second row, right? So they both depend on AK, so you get AK out. This is the process noise. Okay, so if you look at these two, velocity drives the position, right? And this is the same velocity, P dot K plus 1 is equal to P dot K if there's no acceleration, okay? If there's no acceleration. So this is a spacecraft problem. If you look at that, the spacecraft is in the orbit, there's no acceleration, right? So the previous velocity, whatever it is the present velocity, right? And position changes accordingly. But now there is anomaly happens, and therefore there are random gas bursts. That is AK. It was not there earlier. Because of this anomaly, now you get random gas bursts. And now this has not been modeled. So it comes as a disturbance. But the problem is it affects the position, right? And velocity. So we have to bring this into the prediction. Okay, we need to know where the spacecraft is heading now, okay, because of this anomaly. Right. Now, we look at second one. The first one is okay. Second part of the question is this: an anomaly happens in the reaction control system of the spacecraft, which causes the gas thrusters to eject random bursts of gas that results in zero mean random acceleration with standard deviation of sigma a 2 meters per second square. So you are given the standard deviation. So square of the standard deviation is the variance. Okay, right. Now show that the process noise, that is random acceleration, covariance matrix of the system is this. So you have to find the Q matrix, or in fact, in linear quadratic regulators also we have Q, so there can be some confusion. So for the moment, let's take it as it is. You have to derive this matrix from sigma a 2 meters per second square, right? So this is how we do that. Now the process noise, once you model, right, you naturally get to the process noise model, that is T square over 2 AK and T AK, this one. Now, if you know the signal, right, this AK is a random signal. AK is a random signal, but the noise part in the model is not just AK, it is AK T square by 2 for the first row, and it is just AK times capital T for the second row. So it's not just the covariance of the random gas bursts, AK, random acceleration, but there's some sort of mathematical combination here with sampling interval. So when you take W1K and W2K, these are the process noise terms on position and velocity separately, right? When you take the variance of W1 and variance of W2, right? This is how you do that. You get the standard deviation square, and together with it, any other thing that is multiplied. So it eventually becomes sigma A square T to the 4 over 4 for the first row, and for the second row, it is sigma A square and T square. Okay. So this is for the two signals separately, right? The position and the velocity. The unmodeled dynamics of the position and unmodeled dynamics of the velocity, right? They have this type of variance, right? Position and velocity. But now in Q matrix, it's a 4x4 matrix with all these covariance terms in off diagonal. This is the main diagonal, the off diagonal, right? So there you combine position and velocity terms together, right? Where the first term here, right, the far left of position is the variance square, and then get the square root, right? Because it's the same signal, W1. So you get the W1 variance and square it and get the square root. So you eventually end up having the same thing here. T square, T to the 4 over 4 times sigma A square, right? Like that. You get the same signal and square it and then get the root. But here you get variance of the first signal, omega 1, times variance of the second signal, omega 2, right? And then get the square root. Okay? You get the combinations here. So you multiply these two together and get the square root. So when you do that, you will see sigma A square is common again. But if you look at t terms, t to the 4 and t to the 2, when you multiply it, will be t to the 6 and get the square root t to the 3. Okay, t to the 3. Yeah. So this is a symmetric matrix. So on the other side of the diagonal, you have the same thing. And finally, the last term over here, you get the second row, which is the velocity, and look at the unmodeled dynamics of process noise, W2. Look at the variance of it, that is sigma A square T square. Square it and get the square root, and you will end up having the same thing, sigma A square T square. Okay, so that is how you derive the process noise covariance matrix. Okay, right. So that is the second part. Now we move on to the third part. That is position of the spacecraft is measured by the precision gyros at as this equation, ZK equals PK plus VK. So pretty obvious, right? Actual position times the sensor noise, where VK is the zero mean gyro sensor noise. So the sensor has no bias, zero mean, but there's a variance, okay? And that is given in standard deviation form, that is 1 meter. 1 meter standard deviation. So the variance is square of that, that is again 1, okay? Before the anomaly happened, the spacecraft was on stable orbit at equilibrium state at k equals 0. So that is the boundary condition. Okay, stable orbit means you can assume initial position and initial velocities are zeros. Okay, right. And at the first two instance, followed by the anomaly, right, that is k equals 1 and k equals 2, right? Position was measured by the gyro sensors as Z1 equals 0.1 meter and Z2 as minus 0.2 meters, right? This is the position. So it deflects from 0. It goes to 0.1 positive, and the first moment k equals 1, and then it goes the other way, minus 0.2 meters at k equals 2 because of the random gas bursts. Okay. Now use Kalman filter and estimate the position and velocity of the spacecraft at these two instants. Now, did you get the point? It was on the stable orbit at k equals 0, and the anomaly happened. Now there are random gas bursts. So the spacecraft is going back and forth. At k equals 1, it is measured to be at 0.1, but we don't rely perfectly on the sensor. But what the sensor says is 0.1 meters. And k equals 2, sensor says 0.2 meters. Now the problem is, how do we estimate the position of the spacecraft at k equals 1 and k equals 2? Okay, and that estimate would be slightly different from the actual measurement, 0.1 and 0.2. And we expect if you use the Kalman filter, we will get more close estimate than 0.1 and 0.2, right? It will be actually closer to the real value. And in this particular case, we know the real value, actual value, because everything is mathematically modeled. You can use the equations and calculate your actual position and then compare uh, how far away the measurement is and how far away the Kalman filter estimate is, right? This is for us to understand and appreciate what the Kalman filter is doing. But if you do this in reality on orbit, there's no way to figure out the ground truth, actual position. There's no way to find that out. Only thing that is known to you is the sensor measurement. Okay, right. The sampling interval of the spacecraft control system is 1 second. Every 1 second, you do that. Right. Now, if I follow through step 4, the first two random gas bursts are given. That is A0 is 0.15 meters per second square. Okay. The first gas burst is actually known. Maybe it is also measured. Okay. And we assume that to be accurate. And second gas burst at k equals 1 is assumed to be 0.8 negative meters per second square. So these are the accelerations given because of the burst of gas. Okay. So calculate the actual position of the spacecraft, P1 and P2, position at k equals 1, position at k equals 2. And after that, you have to tabulate the actual position, measured position, and estimate of the position, okay, by the Kalman filter. Right. So now we are pretty clear. Let's go to right. So here is it. Now we have the covariance matrix of the process noise. Now we can start with the Kalman filter. Right. So what we do is we take the initial value x hat 0. Okay. And it is 0, 0 because there's nothing given. We assume it to start at 0, 0. Obviously, at this moment, there's no error. Okay. Right. So we consider this as the predicted state at k equals 1. You can see it over here, 1. It is at predicted state at k equals 1. K equals 0, it is 0, 0. Okay, so we take it from 0 to 1 as it is, because initially there's no other way we can do that. Okay, right. Then initial error covariance matrix, that is P1 minus, from that equation, right, we have calculated it to be sigma A square, and this matrix, sigma A is, I think, 2, right? Remember, 2 meters per second square. That is the variance of the process noise, which is given. So 2 times 2, 2 square is 4. And sampling interval is 1, right? So this is 1 over 4, 1 over 2, 1 over 2, and 1. So QB equals 1, 2, 2, 4. You just simply calculated the covariance matrix, the process error covariance matrix. Clear? Right. And also, because you know the system dynamics here, when time equals 1, sampling interval is 1, this is the state transition matrix 1, 1, 0, 1. So that is also known. You can see over here, right? Q is known, phi is known. What about H? H is the output matrix, right? There are 2 state variables here. Out of the 2, we measure only the first one. So therefore, H equals 1, 0, right? H transpose, actually. What about R? R is the sensor noise covariance, right? Sensor noise covariance. It is given as 1. The variance is given as 1. So 1 square is also 1. So we know Q, we know R. There you can see Q is slightly bigger than R, okay? So R is the measurement. So you rely on the measurement bit better. Whereas the process, right, the dynamic model, when you use to predict the future state, the covariance is a bit higher. So therefore, this is a situation where you have to trust the sensor a bit more than your state extrapolation. Okay, right. Next, now you can calculate the Kalman gain, right? This is the third step, right? So I'm not very sure whether you're following properly. The first step is the initial state extrapolation, right? State estimate, and this is priori state estimate, right? That is why this is negative here. And the second step is the predicted error covariance P1 minus, right? Because you have the estimation process. The estimation process has error covariance, and this is that. It is equal to, in fact, Q in this case initially. It's not the case always. Only initially, P1 bar or negative is equal to Q. All right. So as we move on to K equals 1, 2, 3, 2, 3, 4, 5, like that, they will be different. Whereas Q is a constant, and P1, P2, P3, P is the variance of the estimation process. So it's going to change in the future. Whereas Q is a constant. Initially, P1 is equal to Q. Now we calculate for the first time Kalman gain, and this is the equation for the Kalman gain. What do we have there? We have P1 minus already calculated. H1, we know H1 is equal to H because it's not going to change based on K, okay? Right. is 1, 0 anyway. H and P1, H and R1, they're all known, right? They're all known. Just put it in there, right? And get the inverse of that. And you can see the whole thing here. K1 is 0.5 and 1. 0.5 and 1. Okay. That is the third part. And the fourth part is now you estimate the state at k equals 1. And for the first time, you are estimating the state variables, right, at k equals 1. So this is the equation. This is the predicted state, right? From the previous equation, you can see the predicted state, right, is 0, 0. In fact, the initial state itself. That's why we call it predict, right? It cannot be the initial state, right? It should be different. So after correcting, you get it more accurately. So this is 0, 0 plus you have K1 already calculated the gain. Z1 is the measurement. This is given. The sensor tells at K equals 1, the position is 0.1 meter. And you put that thing here, measurement minus H1 and the state estimate prediction, okay? And that is 0, 0. So once you calculate, x1 hat is 0.05 and 0.1. So now see, Kalman filter estimates both states, state 1 and state 2. This is the position, this is the velocity. Okay? And the measurement is 0.1 at k equals 1. But the Kalman filter says 0.05. Okay, all right. Now you update your error covariance, right, using that equation, I minus K1H P1 minus, right? So P1 minus we have already calculated, and you put these ones here. K1 we calculated, H1 is known thing. So the answer is 0.5, 1, 1, and 2. This is the prediction or the estimation process of covariance. Okay, so it's also not perfect. It is zero mean. It is unbiased estimate, but there's a variance, and this is that variance. It is 2 by 2 because the process estimate two states, x1 and x2. All right, so this is the variance of the first one, state variable 1, which is position. This is the variance of the state 2, that is the velocity. Now, if you go to second state, or second instant rather, k equals 2, you have to estimate, or you have to extrapolate from k equals 1 to k equals 2 using state transition, right? So there you are, 0.15 and 0.1. This is the predicted position, predicted velocity at k equals 2. And if you look at the sensor is telling something else for position. And there's no sensor for velocity. Okay, so therefore, we have only the Kalman filter estimate for velocity. Then we have error covariance prediction, P2 minus. This is the equation you substitute for state transition, and then the Q is also known. This is the answer, 5.5, 5, 5, and 6, right? That is P2 minus. So you can see predicted error has higher values, right? Predicted error covariance, right? But we are going to correct it. This is only the predicted value. Then the Kalman gain at k equals 2. This is the equation for the Kalman gain. P2 minus, we already calculated just a while ago. H is not going to change, is 1, 0 always, is output matrix. There you have the same P2 minus, and this is R constant. Now you have gain 0.9 to 0.83, right? If you look at the previous gain, the Kalman gain in the previous moment, it was 0.51, but now the gain has changed to 0.92 and 0.83. So with the gain adjusted, every time you calculate, every time step you calculate the gain and you put it over here with the new measurement. The second moment, k equals 2, the measurement, sensor measurement is different. Now it is minus 0.2, okay, given. The rest you substitute from previous steps and you get minus 0.17, minus 0.19. So that is the estimate at k equals 2. Now, what you have here is that you have the sensor measurement for k equals 1 and k equals 2. Okay, now in this table you can see k equals 1, k equals 2, sensor measurement, right? Sensor is it is 0.1 and minus 0.2. And also you have Kalman filter prediction, that is p hat, right? K equals 1, k equals 2. Kalman filter says 0.05 at k equals 1 and minus 0.1217, sorry, at k equals 2. Okay, right. Now, because we know the ground truth, because it's a mathematical simulation, we can actually calculate the true position at k equals 1 and k equals 2. How? Using the dynamic equation. So this is the process with the unmodeled dynamics. Okay, third term. So for that you can substitute, right, at p equals 0, k equals 0, the position, velocity, and acceleration, right? Put it there, and you will see p1 is 0.075. Put it over here. And when k equals 2, you substitute again what you know and calculate the true value, that is minus 0.175, like that. So now in this table, you have very important information. The true value, true position, Kalman filter estimate, sensor signal, sensor feedback. Now, what is your judgment of this process? Just 3 steps, okay? We haven't gone any far, just 3 steps. It's a bit premature to tell anything, but even now you can see, if you look at the prediction, right? Actual value is 0.075. Prediction is 0.05. Sensor value is 0.1. Okay, so if you look at that, this here the sensor has gone up. Okay, sensor value is higher than the actual value, and the prediction is actually lower than the actual value initially. Okay, but they are equally apart. We can't say anything from here, right? Whether the sensor is better or the prediction is better. Let's move forward. K equals 2. There the true value is minus 0.175 and the prediction is minus 0.17. Very, very close just in the second step. And if you look at the sensor, it's minus 0.2. Now, if you look at that one, minus 0.2 is like 0.025 away from the actual value, whereas the Kalman filter is only 0.005 away from the actual value. So it's getting very close to the actual value. Okay, so that's how powerful Kalman filter is in predicting a true value. Right? Remember, this true value means including the dynamics, unmodeled dynamics. Okay, not only this standard state extrapolation or state transition, but there's this anomaly happen and you model it. So there is some sort of dynamics in the process. Okay, that is not modeled. So Kalman filter captures that. Yeah. Any questions? So now you can bring this further forward, right? K equals 3, 4, 5, 6, 7. Then you will see gradually these two guys are very, very closely apart. So you can actually use the estimate, right? Kalman filter estimate as the true value of the state. And it gives not only the first state variable, but all of the variables. Okay, all of the variables. So this is good because now you can use the state estimate of the Kalman filter as feedback to the control system. If you design a state feedback controller or LQR controller, you need the state feedback, right? And now Kalman filter generates all of these state values so that you can use them for feedback. Any questions, please? All right. So then we are done with this question. Now I want to show you how you do this in MATLAB, right? There are a couple of ways you design Kalman filters in MATLAB. This is the code way, right? You write your code, and the other one is the visual programming using Simulink, right? So first, I'll show it here using how you write the code. So I use a fourth order plant for convenience, right? Fourth order plant, because one of the problems students are having to deal with MATLAB is the matrices, the dimensions, row vectors, column vectors, right? The dimensions, the sizes, bit confusing, right? So you have to be very, very punctual, spot on with what you are dealing with in MATLAB. So I will write the equation here with the dimensions, therefore, right? So there's no ambiguity or unnecessary problems. So I write the equation, state dynamics in the equation 1 here, x dot. So x dot is 4 by 1, okay? It's 4 numbers in a column vector, so 4 by 1. It's coming from x state variable vector ax. So x is same as 4 by 1, x dot. And there's this vector matrix A, which is 4 by 4. All right. So you multiply 4 by 4 with 4 by 1, eventually get 4 by 1. So all of the terms here need to be of this format, 4 by 1. This one, this one, this one, and this one, everyone, right? Because you are adding them together. So this is the transition from state variable from k to k plus 1. Okay, but here it is continuous time. So we have only the rate of change. Okay, we don't have k and k plus 1. This is continuous time. So then the second term in state space is b times u, right? This is the drive matrix or drive vector. U is the control signal, right? So if you have just one single control signal, this is actually just 1 by 1. So therefore b has to be 4 by 1. Because you multiply 4 by 1 with 1 by 1, you get 4 by 1. which is the same size as of here, 4 by 1. So all of these terms need to be 4 by 1. So therefore, you have to figure out what is X, what is U, what is D, what are the things, and then figure out these matrices, size of these matrices. So B is 4 by 1. Then comes the disturbance. Okay. So this is the driving signal. It affects the rate of change. And what about the driving disturbance signal? D, right? So because there are 4 state variables, this disturbance generally affects all of these variables. So there's a disturbance in x1, there's a disturbance in x2, there's disturbance in x3. If you look at the previous exercise we completed, right, this anomaly happens. So it affects the first variable as well as the second variable, right? Position is affected by the random acceleration, and the velocity is also affected by the random acceleration. So therefore, when you write D, the disturbance, you better write it for every state variable. So therefore, it is also 4 by 1. And whenever you have 4 by 1, the Q in front of that, whatever matrix, has to be 4 by 4. Plus, what is this? This is the sensor noise. But sensor noise has no contribution to X dot, rate of change of state variable. So therefore, it is 0. Right? Why I have it here is to satisfy the requirement in MATLAB. MATLAB says it needs to fill this template. It needs us to fill this template. So that's why I put it over here. This is just a 0 vector or 0 matrix. Okay, right. So here you have D, V, Q, and R. D is the disturbance, V is the sensor noise, Q is the disturbance noise covariance matrix, and then R is the sensor noise covariance. Right. The first equation is, I think, perfectly clear now to everybody. And then if you look at number 2, what is this? This is the output equation, y equals cx plus du, familiar to everybody. But in addition to that, I have 0d plus rv. This is the noise coming from the sensor. It affects the measurement, okay? But the disturbance does not affect output, okay, directly. But it will affect the position, x, and therefore it will reflect in y, but not directly. So therefore, this is 0. So when you deal with, when you try to design a Kalman filter in MATLAB using your in terms of coding, you better write it this way, right? Figure that out. And after that, what you do is you assemble all the terms except the first term on the right hand side. So you leave AX as it is, because this is state extrapolation. State goes from K to K plus 1 using this matrix A. But all the other things are actually driving signals Q, D, and V. So you combine these signals together as one single long column, U, D, and V, like that. Their respective sizes are here. U is single input, I just scalar 1 by 1. D is 4 by 1. V is 1 by 1. So it eventually becomes 6 by 1 vector. 6 by 1 vector. And in front of that, you get all these terms, B, Q, and 0. So when you say 0, you better write 0 times B. 0 times B. Okay? Because you're multiplying it with V over here, right? So it should be 4 by 1. This is 4 by 1. This is 4 by 4. This is 4 by 1. When you multiply with 0, it will be still 4 by 1 matrix. So you just can't say 0 because these are matrices. So it has a structure, dimension. So if it is 0, you have to fill the dimension of that one array or matrix with all zeros. That's why you write it this way. Then you can define this whole matrix here as B star and this whole column here as U star. Now it looks like x dot equals ax plus bu, very familiar format to everybody. Okay. Now remember, this B is not the B used to be, and U is not the U used to be. They're different. But now you can see them as consistent pattern. Equation number 3. Similarly, if you look at Y, you can write Y as Cx, take it as it is, but the rest du 0d plus r v, you can write it like this, and u dv, the same vector over here, right? U star, same vector here, but take all the terms, d from here, 0 from here, r from here, and fill this vector over here. This is a matrix, right? Then you give it a name d star, and this one u star. So eventually you have equation 3 and equation 4, which are actually similar in appearance to state space model continuous time, right? X dot equals x plus bu, and y equals cx plus du, right? In MATLAB, this is how you design your system with disturbances, process noise covariance, and the sensor noise covariance. So now, because you know A, C, Q, and R, right, you can actually use the LQR command, linear quadratic regulator command, using these arguments, A transpose, C transpose, Q, and R, the whole thing transpose, and it will generate the Kalman filter block in MATLAB. Kalman filter is a block in MATLAB. When you launch this command LQR with these arguments of A, C, Q, and R, because you already know these values, right? A, C, Q, and R. Q here, R there, A and C are here. So with that, you can launch this command, LQR command. Watch out these transpose and all that, because that's a requirement by MATLAB, right? To make the computations efficient. It generates the Kalman filter. Okay, you generate the Kalman filter in MATLAB, and then after that you generate the Kalman filter system. This is a slightly different version of just KF, right? You transform this as to a state space model using SS command. The block diagram, or the transfer function, can be represented as a state space model also, right? So this Kalman filter block can be converted into state space model, right? We will give it a name like syskf. Now you use the state space model SS, and you give it A minus kf times C, B times kf. This is identity matrix of 4, 0 times B kf. So if you look at that, it is over here, right? You can see A star, A, B, B star, C, and D star. Okay. So if you remember, if you recall this A minus kf times C, right, the state feedback, and B and kf identity matrix, and again B and kf. If you put this format, you get the system based on the Kalman filter. Now below here you can see this diagram. This is the Kalman filter state estimator. A minus kf times C, B and kf identity matrix, because this identity matrix means you are taking, or you are producing all 4 state variables, their estimates, S hat 4 by 1. This column is produced by this system. Okay, it's a state space model. You can see A, B, C, and D. This is actually C, identity matrix. Okay, right. So for the Kalman filter to produce the states, to estimate the states, you need to give the control signal and the output, the measurement. Okay, whatever measurement you make out of the plant using a sensor, you have to give that to the Kalman filter and the control signal. Then it will produce the states. Once you have the states estimates, right, you can use the Kalman filter KLQR, the gain, right? This is the LQR gain, not the Kalman filter gain, right? LQR gain for state feedback. You bring it over here. This is the control signal, U, right? And this U, now it is U star, in our model, U is actually U star now, okay? So this U is just one of the elements. It's just one of the elements. There are other elements also, right? This is the disturbances. This is the sensor noise. They're also coming in, combining with U to produce U star. So this combination is happening over here. You have D's and V. All of the sensor, the process noise, random process noise are here. And this is the sensor noise. Together with that, you have U. This is the state feedback control signal. This all of these signals together produce U star. And U star goes to A, B star, C, D star. This is the augmented plant, right? With the disturbances, the sensor noise, all of that. It produces YT. So this is more realistic simulation because you used to do like AX plus BU, CX plus DU thing, right? You did not consider the sensor noise or the process noise. Now you have all of this in your simulation. So what you are simulating here is more closer to reality. So you have this true signal, YT, true output, just one output, first state variable. It goes over here to the Kalman filter, estimator. And also the control signal that is given out by the LQR, right, controller, this is the controller, is also fed back to the Kalman filter. And the filter produces the state, estimate the state. So this controller, LQR, I think I mentioned some time back, what it does is that it uses two matrices, one for the state variables, right? There are four states here, four state variables. And we give it a weight matrix 4 by 4. And along the diagonal, you can see the weights given 100, 20, 20, 30. This 100 means the first state variable, the variation of the first state variable is very costly. This 20 and this 20 means any variation of the second and third state variables are not that costly, so that you can allow some variation. Doesn't matter too much. This 30 means the last state variable, any variation in that state variable is costly, but not as costly as the first variable. Okay, we are telling that to the LQR controller to calculate optimal gains. Okay, and also we say WR, that is the weight of the control signal, is given 5, which means compared with all of these four state variables, the control signal is not very costly. It's the least costly signal here, which means you can have very high control signals, right? It's not very costly. So when you operate a plant, you generate a control signal, and also you get your state variables, right? In LQR design over here, right, we have the provision to specify in MATLAB how costly these signals are, how costly to generate the control signal, and how costly the variation in the state variables. Right? These numbers tell that, and it may have some rationale behind it, or it can be arbitrary. You make your best choice here, right? Now with that, we can run this control system and see for ourselves what is happening. And also when you're running, you can change these values if you want, right? If you understand, okay, none of this is not correct. Control signal is very costly. To generate controls, you need to consume energy, right? Petrol, gasoline, or electricity, or whatever. So therefore, this has to be 100. And these signals can go up and down a little bit, doesn't matter too much. So you can reduce this 100 to about 50, right? These signals are like, this is the error, right? If it is an air conditioner, it is the difference between the actual temperature and the reference temperature. And if you are really concerned about this error, you can have a higher value here, like 100. Okay, keep it there. Other things you can reduce. This is a MATLAB Simulink model. By the way, we'll take a little break over here, and after the break, I'll explain you the model and the rest of the lecture. Okay, welcome back. Well, can you see my screen?
Yes, sir.
Right. So please pay your 100% attention here, right? I want you to be able to draw these Simulink block diagrams and implement a complicated system, just like what you see over here. So, right, now you have two systems here, right? This is the plant. As you can see, it is x dot equals ax plus bu, okay? And y equals cx plus du. This is the augmented full output plant. Right? This plant gives you all four outputs because the C is a 4x4 identity matrix. So it produces all four, right, state variables. In fact, we are dealing with a fourth order system, four state variables. Okay. Because you need all four states here, this one line has all four states, x1, x2, x3, and x4. And here you split it using demarcs, right, into four separate lines. And in the first one, this is probably the position, right? We tweak it a little bit, adding another offset, right? This is actually the reference. If you want the system to follow a reference, you can put it over here. Otherwise, it will be 0. 0 means whatever comes through this line, the LQR will try to reject it. Any non-zero value coming from here, it tries to control using this control signal. It tries to reduce that. LQR is a regulator. It tries to bring all state variables, all of them, to 0. Okay, that is the whole purpose of LQR. Now what we do is, we want LQR to bring all these three states to 0, but we want the first one to go to the reference. So therefore, what we do is we deduct the actual reference. Let's say we want reference 1, we put it like negative here. So it will be -1, right? If you get it over here 0, actual 0, it comes as -1 over here, and the LQR will try to bring it up to 1, right? So then the first state variable moves up to 1. So when it is 1, this is 1 minus 1 is 0, then LQR is happy. He thinks state variable 1 is at 0, but actually it is at 1 at the reference value, right? Okay. Now these are blocks in MATLAB that allows us to send the variables to the workspace so that we can plot and record or do all kinds of things. Right. So this is one system. The other system, okay. For that also, this is augmented full output plan. So the U is not just this U, but you have unmodeled dynamics, right? D1, D2, D3, D4 that we discussed. And also you have the sensor noise, that one also. Can you see it over here? Process noise 1, process noise 2, 3, 4, 4 states, 4 process noises, right? Unmodeled dynamics. This is just like the random acceleration of the spacecraft, okay? And also the sensor noise comes over here, added together, right? It will produce this U, actually this U star, okay? Fine. Now we have a second system over here, which is augmented SISO plant, because we don't have all 4 states available for measurement, right? Available for feedback rather. Because if you want to do it that way, you got to have 4 sensors here, 4 separate sensors. It's expensive. Usually we measure just one, the most important variable, which is x1 probably, right? So therefore, this is SISO plant, single input. Sorry, this is not SISO. We can say it is multi-input, single output, all right? Because there are multiple inputs over here, as you can see. This C is just a vector 1, 0, 0, 0. It's a row vector. So that when you multiply with x1, x2, x3, x4, you only get x1, first variable, as y. Now the problem is you cannot use this one for LQR, because LQR needs 4 states. LQR is a state feedback regulator, okay? So you need to provide LQR all 4 states. So what you're going to do is that you're going to put a Kalman filter here, right? The Kalman filter will read the whatever available sensor reading. You have to tell which one it is using this C. Then Kalman filter knows, okay, I'm getting first variable or the second one or the third, whatever it is, right? And also you have to give it, give the Kalman filter the control signal also. Then the filter produces all 4 states, right? And then again, you can put this reference signal as an offset to the first state variable, then everything will work fine. Okay, the 2 systems. So I can show you this in MATLAB. This is the actual MATLAB Simulink block, and this is the code. In the code, you can see the system matrix has components, right? And drive matrix has a component. This is the transfer function, A matrix, B, C, D, state space model. This is the simulation time constant, discrete time interval 0.1, and this is the total duration 150 seconds. And you generate the time vector for the simulation. This is Q and R, right? Using the standard deviation, you generate the covariance. This is the that one, covariance matrix. This is the sensor noise covariance. This is initial condition reference value, the offset in the LQR. This is the LQR gain matrices for the state variables, and the control signal. It's just 0.1, right? Very small for a reason. I put it 0.1, which means essentially weight of the control signal, right? So the cost of the control signal. Then this is the LQR command that you generate using A, B, W, R, Q, and WR. this is the augmented system BD and DD. This is augmented state space model. This is the true plant from where we get the true signals, right? And the Kalman filter is designed here, and the Kalman filter as a system block state space model is over here. Then you open the Simulink block I showed you just a while ago, and you simulate it, and then you plot the results, right? So once you implement it, it runs and it produces results like this. So what you see over here is that it's too small. There you are. You can see what x1 true in blue color. That is the true output, the first state variable, and the red one is the estimate of that. Is the Kalman filter. You can see very close to each other, right? It's not exactly one. The reference is one, of course, but it just swing around it because this is now very noisy system, right? A lot of disturbances, 4 random signals, noises coming in. Actually 5, the sensor reading, including the sensor. But Kalman filter has been able to predict the estimate the state very accurately. I can see it over here. If I zoom it up, right, you can see it like that. But you don't see the level being maintained. It goes up and down around 1. Okay. So this is the reality. Most of the curves that you have seen earlier are like hypothetical or ideal conditions, very flat curves, maintaining the 0 steady state error like that, right? Hardly found in reality with noise and all. And this is the control signal. You can see it goes up and down, right? It's a kind of restless signal. When you deal with a lot of noise and a lot of estimations, this is pretty much the commonplace scenario. What about the other signals, X2, X3, and X4? Kalman filter predicts all of the state variables, not only the first one, reasonably, right, but not perfectly. You can see it over here. There are differences, right? But it's a quite a significant performance here, right? Without this filter, you are unable to implement the state feedback because you have only one sensor. It also has some noise. So using that single sensor and predicting all the other state variables so that the estimates are used by the LQR for state feedback, and you somehow maintain the system, control the system in a reasonable manner, right? So that's why it's so celebrated work by Rudolf Kalman, right, in 60s. Right now, if I want you to play around with it. So let's say I change, say R for example, the WR, this one, right? This is the cost of the control signal, cost of the control signal. And now if you can see it's no cost, it's 0.1. If I put it, if I increase the cost, say to 50, what will happen? Right, give me the answer. Anybody? Now I'm telling to MATLAB, design the LQR controller, right? So I can show it over here. This is the LQR controller here and here, right? Now I'm telling the control signal is so expensive. So therefore, I don't want to generate huge control signals, right? But small control signals, right? So what do you expect? What do you expect as a result? I want your answers. Anybody?
It will take some time to stabilize.
It'll take time to stabilize. Okay, right. Any other answers? Chamira, what do you think? What would you expect when we say control signal is expensive, so we don't want to generate huge control signals? Chamira, are you there?
Yes, sir.
You have no idea. Okay. Think about it and let us know. Chaturanga, what do you think? Chaturanga, are you there?
Sir.
Yeah, are you there?
Yes.
Yeah. What do you expect? What will happen to the result when you increase the cost of the control signal? No idea? Dilan?
Yes, sir. Yeah, I have no idea, sir.
No idea?
Exact answer, yeah.
Okay. Heovasan?
Sir, so it will take time for to give a stable response.
It will take time. Okay, right. Dhananjay, what do you think?
I'm the one who answered in the first.
Okay, all right. Sulochana, what do you think?
Yes, sir. It will take some time to respond.
Oh, Sulochana, sorry, Sulochana. Right. It will take time. Right, right. Okay. Vijay Tilaka, what do you think?
No exact ideas about that.
Right. Now, this is interesting. Now, think about this. In a way, this is common sense. Now, you are controlling something, and there is an objective. That's a reference that you want to achieve. Okay. So, you can achieve what you want to achieve by providing a control signal. Okay. Right. Fine. Now, if you are unable to generate healthy, substantial control signals, you are unable to achieve the objective, isn't it? Very simple. Very simple, right? Now, you are in a situation like that. Now, this control signal system, the objective is to track the reference. There's a reference value. And the system response has to follow the reference. If you cannot generate enough control signal, you are unable to track the reference. Simple. Don't think so complicated way, right? Think very simple, accurate. Okay. You cannot achieve your objective if you cannot generate sizable control signals. Okay. Right. Now let's see whether that common sense resonate in the answers, right? Now this is the result now with a higher cost for control signal. Right. Now you can see the X1, right? X1 is the the response, right? Actually, the first state variable, and the reference is 1. Hold on a second. So let's go back to the reference. What have we put there? There's the reference. Can anybody see the reference? Yeah, there you are. X reference is 1. Okay, X reference is 1. Right. So now the 1 is over here. 1 is over here. X1 is far too low. Can you see that? It is, in fact, oscillating because of noise and all that, but it is roughly around 0.55, somewhere here. It cannot get to 1. This is exactly what we eventually expected, right? But I didn't get your answers from you. But this is the common sense thinking, right? It is the control signal that will bring it up to this level. And after that, it will like go up and down. So your answer that it will take time to settle is not very correct. Even though it takes time, it will never get to 1. Okay. So you got to generate healthy control signals if you want to achieve the objective. If you want to track the reference, it's important that you generate sizable control signals. So therefore, if you penalize the control signal by increasing WR over here, that's not very correct. So we have to reduce this to, let's say, 10. Let's see what will happen now. Now 10 means not very big cost. So we ask MATLAB, okay, you can go ahead and actually generate a bit higher control signals. Now you can see it is improving, right? It's improving. Can you see that? It's getting closer to 1 gradually. So this is how you design your LQR, okay? And also it's very important that you are able to interpret the results that you see on screen in feedback control systems, right? Why it is happening this way, why it is not happening that way. And if I change Q, what will happen to the error? If I change R, what will happen to the error? And so this kind of this knowledge about all these things, how they are related, is extremely important. And you can only get that knowledge if you engage yourself with MATLAB, write your codes, and test it for yourself. Okay. Right. So now let's go back to the slides, right? So this is the question I asked you: y equals x1 doesn't climb to reference 1. Why? So it doesn't climb there because the LQR controller we use here, we have high cost assigned for control signal, so it doesn't generate enough control signal. So here we have different values for the cost of the control signal, starting with 20, 10, 1, and 0.1. So today we started with 0.1, which is what I left with at the end of the simulation sometime back. So that's why you got somewhat better performance up front, but when you increase the cost for the control signal, you saw the deterioration of the signal, right? Error increased. WR20, the weight for the cost when it is 20 is the worst here, but gradually increasing when you have lowered cost for the control signal like 10, 1, and 0.1. All right. Right.
Sir, they are
Yeah.
questions, sir. They are when you are selecting that cost function, that cost value, is there any specific value to select, or we are modeling to that given cost function, cost value?
Yeah. So usually the common practice is that you start with something arbitrarily, but with some sort of rationale, and simulate it and see it for yourself, and then tweak a little bit, right? Increase and decrease the cost for the state variables, and here the relative cost for state variables and the control signal, and with a bit of an attempt, right, and bit of simulations, you can get something really reasonable, right? Versus the other way is somehow connect these gains into the performance, like an analytical way, and then try to develop a closed form solution. So that is quite complicated. That's quite complicated. For certain class of problems, it might work, because this is going through a control loop, right? So you have to analyze the entire loop, and it's like the first order system. Remember second order systems, right? You have the rise time, overshoot, etc. That type of closed form solutions, equations, you cannot write over here. It's a bit too complicated. So therefore, usually what we do is we pick up the values arbitrarily, right? And then try to manually tune it.
Got it, sir.
Okay. Right. Today I want to wind up a little early, so therefore we'll leave the extend Kalman filter for the next week. How many weeks do we have? Just 1 or 2?
Means to the end of the semester.
Yeah, maybe we need to have another one, just one class, okay, to wrap it up. So we'll meet up next Sunday, the last class. All right. So I'm gonna wind up today, and hope to see you next week. And if you don't mind, we can do a little bit extra next time, right? And try to solve some of the past paper questions so that you can get some idea of the paper and all. So we'll do it that way. Is everybody okay with that?
Yes, sir. It's okay, sir.
Right. All right. Let Amit know about it. Okay. So I'll see you next week then.
Okay, sir. Have a good evening and a good week.
Good evening to you.
Thank you.
All right.
Thank you, sir.
Thank you, sir.
Thank you.
Yes, sir.